Welcome to AI Paper Podcasts. Today, we're diving into the Youtu-LLM technical report from Tencent Youtu Lab. And this paper, well, it makes a pretty profound claim about the scaling laws we all thought we knew.
It really does. It challenges that whole orthodoxy that bigger is always better. Their mission here was all about efficiency, to create a really powerful but lightweight agent without the massive costs of today's giant LLMs.
And the result is, frankly, pretty shocking. We're talking about their Youtu-LLM 2B model that's just 1.96 billion parameters.
Tiny by today's standards.
Right, and yet it often matches or even surpasses models 2 to 4 times its size, things like Qwen 3.4b or even the 8 billion parameter DeepSeek R1 Distill Llama. So how is it possible that a 2B model is beating an 8B model, especially on these tough reasoning and coding tasks?
And that's the key question, really.
Yeah.
They essentially found a new scaling axis. They unlocked this performance with 3 main pillars. First, there's the architecture. They chose the very efficient dense multi-latent attention, or MLA. Second, a really unique multi-stage pre-training recipe they call Commonsense-STEM-Agent.
And the third piece, which I think is the real innovation here, is this obsessive engineering of huge amounts of structured agentic trajectory data. They call it Agentic COTI. And it's designed from the ground up to teach the model how to plan, act, and reflect.
Exactly. It's a powerful argument that, data quality and structure can actually trump sheer parameter count. It's about intelligent design, not just brute force.
This feels like it's tackling a huge, immediate problem for the whole industry.
Oh, absolutely. The state-of-the-art models are just colossal. We're talking tens, hundreds of billions of parameters. And that translates directly into massive costs, computational, financial, environmental.
Which limits who can even play in this space, right? Especially if you need something that's fast or can run on a device that's not in a massive data center.
Precisely. It kills accessibility. And most existing small models, the ones under 7B, they've always relied on distillation or just instruction tuning.
And that's a bit of a shortcut, isn't it?
It is. It's effective for making a small model act like a big one, aligning its output. But it doesn't really give it the underlying cognitive skills.
So they end up being a bit brittle, they lack robustness, they can't generalize well, and they really struggle with the kind of multi-step planning you need for, say, a complex coding task or deep research.
Yeah. The small model knows what to say, but it doesn't know how to think through a problem with multiple steps. The Youtu team wanted to change that. They wanted a lightweight model with those agentic skills baked right in.
Intrinsic competence, not just mimicry.
Exactly. Planning, execution, perception, reflection, all native to the model.
Okay, so we've got the why. A great recipe needs a great oven, though. What did they pick for the architecture to make this small model so competitive?
They went with dense multi-latent attention, or MLA. The model itself is 1.96 billion parameters, 32 layers. And choosing MLA over something like a mixture of experts or MOE model is a very strategic decision.
That's interesting. We hear so much about MOE models being efficient. Why avoid them here?
Well, MOE is great for training efficiency. But for inference, especially on, say, an edge device, it can be a real headache. You have all these I/O operations swapping experts in and out, which creates latency.
So it cancels out the speed advantage?
It can, yeah. MLA, on the other hand, boosts performance on a constrained parameter budget using things like low-rank compression of the KV cache. It's just a better fit for this kind of on-device scenario.
So for any engineers listening, that means better real-world performance, lower latency, less power draw, a smart choice for the target environment.
For sure. And they didn't stop there. They also put a ton of effort into their tokenizer.
That seems like such a fundamental detail, but it sounds like it made a big difference. What did they change?
They got really strict with their pre-tokenization rules. For one, they segmented all Chinese characters in CJK punctuation. But the really critical part for reasoning was how they handled numbers.
Okay, what'd they do?
They only kept the atomic digits, 0 through 9. They completely avoided creating tokens for multi-digit numbers like 42.
Why is that so important for reasoning?
Well, if you tokenize 42 as a single unit, the model just sees it as an opaque concept. But if you force it to see 4 and 2 separately, it has to learn the actual rules of arithmetic and positional value. It builds a much deeper numerical understanding.
And that paid off?
Big time. They saw about a 10% gain in efficiency on reasoning data compared to other tokenizers like Qwen 3s. That's a huge win before you've even started training.
Wow. Okay, so then on to the pre-training recipe itself. You mentioned this Commonsense-STEM-Agent idea.
Right. It's a very intentional, layered approach. Think of it like a curriculum that gets progressively harder.
Walk us through the stages.
Stage 1 is the foundation, all about common sense. They used 8.16 trillion tokens, mostly from the web and encyclopedias, to give it broad world knowledge.
Makes sense.
Then stage 2, the STEM boost. Here, they cranked up the proportion of STEM encoding data to about 60%.
Shifting from knowing things to understanding how things work.
Exactly. Stage 3 was about giving it a bigger memory. They extended the context window from 8K up to 32K, and then all the way to 128K tokens.
So it can handle really long, complex problems.
And then came stage 4, the Agentic mid-training, or AMT. This is where they introduced all that special trajectory data. But what's really fascinating is when they did it.
What do you mean?
They found that doing this agentic training after the long context training was already established gave them way bigger performance gains.
So the model needs to have that big memory capacity before you can effectively teach it complex planning. That's a huge insight.
It is. Which brings us to the core innovation here, their whole agentic data engineering paradigm.
Right. This is where they're really cultivating those cognitive skills, and it's all built on this idea they call agentic COTI.
Exactly. They looked at traditional chain of thought, COTI, and saw that it often leads to what they called overthinking and unnecessary repetition. It's just too linear.
So what's their fix?
They replaced it with a very disciplined sequential reasoning structure using XML-style tags.
So instead of just a stream of consciousness, the model has to follow a strict workflow.
It has to. The sequence is analysis, then plan, action, reflection, and finally a summary. It forces the model into this agent loop. Self-correction is baked in from the start. They generated 25 billion tokens of just this structured data.
And you can see that structure applied in their specific domains, like mathematical reasoning.
Oh, absolutely. They built 1.38 million math trajectories. They broke down math ability into 11 atomic skills like theorem application, self-reflection, and then synthesized solutions following that strict plan-action-reflect loop.
That case example they gave about the number ring with the square root of 3 was really telling.
That's a really high-level problem. And the model doesn't just jump in. First, it does a semantic analysis and realizes the term number ring is ambiguous. It could mean a standard ring or a field.
Wait, so the model actually argues with itself about the definition before it even starts solving?
Yeah, it decides a direct proof is risky and that a counterexample-oriented approach is better. That level of strategic self-reflection is just not what you expect from a 2B model.
It's incredible. It shows real judgment.
It then goes on to construct the answer and verify it under both interpretations. It's really thinking.
Okay, let's talk code. 70 billion tokens of code trajectories. And here they had this really clever strategy for scaling actions by branching both successful and failed attempts.
This might be the most innovative data engineering trick in the whole paper. So they identified critical actions, basically the editing and testing steps where a decision really matters.
Right. And normally you'd just throw away the failed attempts.
Exactly. But they kept them, which sounds risky, right? You don't want to teach the model bad habits.
For sure. So how did they avoid that?
They don't reuse the failure itself. They reuse the path leading to the failure. They take a failed trajectory, chop it off right before the bad decision, and then generate a new, better branch from that point.
So they're basically telling the model, your logic was good up to this point, now let's try a different path.
Precisely. They're enriching the model's action space and teaching it what not to do, all while reusing valuable data. It's an incredibly efficient way to teach resilience and debugging.
Okay, and the last big category was deep research trajectories.
Right, for things like multi-hop Q&A and generating reports. For open-ended tasks, they built what they call a think twice framework.
What's that for?
It's to fight against insufficient investigation bias. You know how LLMs can sometimes rush to a conclusion without gathering enough info?
All the time.
This framework forces the model to pause, summarize everything it's found so far, and then explicitly evaluate if any section needs more digging before it's allowed to write the final report.
It mandates thoroughness. I like that. They also mentioned inverse trajectory synthesis.
Yeah, this is super clever. Instead of starting with a question and generating a messy path to an answer, they started backwards from high-quality, verified sources like academic papers or legal documents.
And used the citation graphs to work out the reasoning steps that must have led to that correct output.
Exactly. It ensures the trajectories are factually grounded from the start. And across all of this, the best training strategy they found was something they call aggressive masking.
Let's unpack that. It sounds important.
It's crucial. They found they got the best results when they masked out the tool's response, the system prompt, and the user's query during training. They focused the loss function entirely on the model's own internal reasoning and action generation.
So they're basically forcing the model to focus on its thought process, not just the final answer or the external context.
That's it. It minimizes noise and forces it to learn the structure of good reasoning.
Okay, so after all that pre-training, they move on to supervised fine-tuning, SFT.
Right, and they did it in 2 stages. Stage 1 was called Reasoning SFT, and it was deliberately skewed with 40% math data and 30% code data.
Why that heavy focus on logic?
The idea is to cold start the reasoning engine, solidify that logical core before you move on to more general instruction following.
And then stage 2, the general SFT, brought in more variety.
It did, but crucially, they kept reintegrating the stage 1 data to prevent catastrophic forgetting. And this is also where they trained in a really neat dual-mode capability.
The thinking and non-thinking modes.
Exactly. They took some training samples and just stripped out all the intermediate reasoning steps.
Yeah.
By doing that, they taught the model it could either give a full, transparent breakdown in thinking mode or just a fast, concise answer in non-thinking mode, all controlled by a simple token.
That's a huge bonus for deployment flexibility.
It really is. Then for the final polish, they use reinforcement learning with a big focus on stability.
Why was stability such a big concern?
Well, with these long, complex reasoning chains, training can go off the rails pretty quickly. They made 2 key choices. First, they found that using FP16 precision actually worked better for them than BF16 in terms of prediction stability.
That's counterintuitive. Usually it's the other way around.
It can be, but for their setup, FP16 gave them higher fidelity. Second, they implemented something called consistent sampling.
What does that do?
It's basically a strict quality control filter during training. If the difference between the model's prediction probability during training and inference drifted too far beyond a tiny threshold, they'd just discard the whole batch.
Wow, that's strict.
Very. But it dramatically improves stability and let them train for longer without performance plateauing, especially on those tough math and coding tasks.
And the results speak for themselves. The base model, even before instruction tuning, was competitive with the much larger Qwen 3.4b.
It was. But the instruct model is the real headline. The Youtu-LLM 2b instruct beats the bigger DeepSeek R1 Distill Llama 8b on a lot of execution-heavy tasks.
Looking at the benchmarks, yeah. 95.9% on human evil, 85% on MBPP. That's incredible for a model this size.
It really confirms that this specialized structured training allows a smaller model to punch way above its weight, particularly where precision matters.
And the ablation studies on the Agentic mid-training stage really sealed the deal, right?
They did. Adding that stage gave them a 14.4% average relative improvement on agent benchmarks. It's definitive proof that this method of teaching long horizon planning and error correction actually works.
So it's clear the big takeaway is that data engineering, specifically this focus on high-quality, structured trajectory data, can be a more powerful lever than just adding more parameters, at least for these kinds of specialized agentic skills.
Absolutely. But they're also realistic. They acknowledge there's still a gap compared to massive proprietary models, mainly due to resource constraints. Their future roadmap is pretty ambitious, though. They want to evolve this into a proper world model.
One that doesn't just plan, but can simulate the results of its plan before acting.
You got it. And they're also looking at new architectures like diffusion LLMs to tackle the latency that can come with these long, detailed reasoning traces.
It's an incredible piece of work. They've shown that focusing on structured thought can be a new and powerful scaling axis, one that doesn't just rely on throwing more and more compute at the problem.
And that really brings up a critical question for you, for anyone out there building these systems. They found a clear saturation point with their math data, where adding more volume actually started to hurt performance because of data imbalance. So it makes you wonder, where does the optimal balance really lie between just increasing data volume versus rigorously refining data structure? That trade-off between quantity and structure is probably going to define the next generation of efficient, capable agents.